Okay, so we are looking at the course outlines then on page 15, and we are primarily focusing on chapter 5 with just a couple things, as I mentioned, out of chapter 4. And so just to recap of where we left off last time, so we were studying last time inorganic molecules, and those would be different from organic molecules because anybody remember what two elements organic molecules have? Yes.
Hydrogen and carbon.
Excellent. Hydrogen and carbon. So we're really a bunch of hydrocarbons. So we have these long carbon skeletons with hydrogens attached. Does anyone remember what kind of bonds those are that hold these hydrocarbons together? Covalent, exactly. So these are all covalent bonds, which remember they are sharing electrons or strong bonds within that molecule, and they make up these large biological molecules that make up us. So essentially, what are we when it comes to molecules? We're a bunch of proteins, carbohydrates, lipids, and nucleic acids. Nucleic acids that are the NA that you hear about in DNA, deoxyribonucleic acid, or RNA, ribonucleic acid. So those are the main molecules we're looking at now. So last time we were looking at very important inorganic molecules, things like water. Even though it's not a hydrocarbon, it is essential to life, as we mentioned. And they come together, again, to form these large biological molecules of life. So this is what we call organic chemistry. It's a study of carbon compounds, and if you take organic chemistry, you're going to spend a lot of time looking at these hydrogens and carbons and their different kinds of structures. So we just call them hydrocarbons for short. And looking at some of these, you can see that they can be in carbon chains, as you see here. And again, these dashes representing single covalent bonds. What do the double lines mean? Double covalent bonds, exactly. You could even have triple covalent bonds. A lot of these also form branched chains, as you see here, or even carbon rings. So we're going to see all these different structures, and if you take organic chemistry, you spend a lot of time studying these structures and learning how to actually draw them. But so what makes one hydrocarbon different from another? It really has to do with what else is attached to this carbon skeleton. So we have what are known as functional groups, and these are groups that, as the name implies, cause that molecule to behave or function in a certain way. And so if you take something like a lipid and mix it with water, is it going to mix? If you put oil in water or wax in water, it doesn't mix. So what does that tell you? It's hydrophobic or hydrophilic? If it doesn't mix. Hydrophobic, exactly. What makes it hydrophobic? These functional groups. So these functional groups are very important. I'm going to mention a few right now, but again, I don't ask that you know these yet because as we go through the course, we'll come back to many of these. But a few that we're going to be looking at in the course are, first of all, this hydroxyl group. So when we studied inorganic acids and bases, we looked at that OH group and we called it the hydroxide group, and if a molecule has that attached or has that something like sodium hydroxide has that OH group, we called it a base. Well, when it comes to organic compounds, if they have this OH group, we call them an alcohol. And so here's an example of ethanol. This is a typical alcohol in alcoholic beverages, has that OH group. The carboxyl group is another important one. We're going to see this quite a bit. It's this C double bond OOH group right here, and when that's attached, this is what we call an organic acid, not to be confused with an inorganic acid. An organic acid is named an acid because it's got this group, and again, it has to do with hydrocarbons. So when you have this group attached to anything, we use the name acid, like acetic acid you see here. Or it might be fatty acids we're going to look at have that group attached, or nucleic acids have that group attached. So we'll be coming back to that one. We have amino acids that have the carboxyl group as well as this amine group, which has a nitrogen as part of that very important group. And so when we look at amino acids, they have an amine group and an acid group. Anybody know what amino acids build? They're the building block of proteins, exactly. So we're going to talk quite a bit about those as well. And then this very important group, phosphate, which has this phosphate bond shown here in yellow. Usually textbooks represent them in bright yellow because they're highly energetic. So we're going to see a molecule called adenosine triphosphate, 3 phosphates, because in each of those phosphate bonds, a bunch of energy is stored, and that's our energy carrying molecule in the cell. So ATP, we'll talk about that also. So there's just a few of the important functional groups that we're going to be talking about as we go through the course. So what is a macromolecule? What does macro mean? Big or small? Big, right? So again, we're saying we're putting all these little molecules together to make these huge, diverse macromolecules. And macromolecules are also known as polymers. What does poly mean? Many or few? Many. So if you have a polymer, that means many molecules all attached together. That is a macromolecule. Polymers are formed from monomers. What does mono mean? One. So we take these unit molecules called monomers and link them together through chemical bonds, mostly covalent, right? And form polymers. So a polymer is a macromolecule. The monomers are often referred to as unit molecules. Those are the building blocks. Like we just said, amino acids build proteins. Amino acids would be the monomers. Proteins would be the polymers. So we have 4 classes of these organic molecules we're going to look at. And as I said, if you break us down and say, what are we? We're really a bunch of carbs, proteins, lipids, and nucleic acids, and of course a lot of water. Carbohydrates, these are all the macromolecules. Carbohydrates are made of the unit molecules known as simple sugars, or monomers, usually monosaccharides. If you hear the term saccharide, that refers to sugar. And in fact, our first sugar substitute was called saccharin. So if you have a polysaccharide, it's a complex or polymer of a carbohydrate. If you have a monosaccharide, it's a simple sugar. Proteins are made of amino acids. And so proteins are the polymer, amino acids are the building blocks or monomers. Lipids actually are made of 2 unit molecules, fatty acids and glycerol. So usually folks, when we're eating, what we get in our diet are either the macromolecules. Usually we're eating proteins, carbs, lipids, and all cells have nucleic acids. Why do they all have nucleic acids? Because all cells have DNA and RNA. So it's a small amount, but still. So what we get mostly in our diet are carbs, proteins, and lipids. And then when we eat them, we digest them down into their unit molecules before they can be absorbed into the cell. So we digest them down into simple sugars, amino acids, fatty acids, and glycerol. And if it's nucleic acids, we break them down into nucleotides. That's a building block of nucleic acids. And then it's small enough now in its unit molecule form or a monomer to get into the cell where we can use it for whatever we need. For example, if we need energy, which one of these 4 would be the best for that? Carbohydrates, quick source of energy, right? If we store energy, we store it in the form of what? Lipids, exactly. That's how, if you eat more carbs than your body needs for, considering how much energy you require, if you eat more carbs than the energy requirement, it's going to store it as lipid, and that's how you can end up literally getting fat because you're storing all that excess. So you want to balance out your intake versus your energy requirement of these nutrients if you wanted to maintain weight. And of course, if you were trying to gain weight, you just do that. Or gain weight, you do the opposite. Okay. So what we want to look at next is how we make and break these molecules. So when we eat, we're primarily breaking our food down. We're mostly getting complex macromolecules, and we're going to digest them down. And the word for that is lysis. Lysis means split or break. And in that case, we need water to do it. So we are going to hydrate, add water, right? If you hydrate something, you're adding water. If you dehydrate, you're losing water, right? Ever been dehydrated? What's the first thing you do if you're dehydrated? Drink some water, right? So there are 2 opposite reactions. We have synthesis and hydrolysis. Synthesis actually means building, and as you see there, it is a dehydration process. So in dehydration synthesis, this is actually building. This occurs when 2 monomers bond together, and notice it is dehydration, so water is a product. Remember, in a chemical reaction, the arrow always points towards the product. So if the arrow is pointing at water, water's coming out, it's a product, that's a dehydration synthesis reaction. And then just the opposite is true. What if we need to rebuild molecules? Then we have to, not rebuild, but break molecules down. Then we need to lyse them. The word lysis right here means splitting. And to do that, we have to add water, hydrate. So hydrolysis is when we take polymers, break them down to monomers, and it's, again, reverse of the dehydration reaction, so water is a reactant. The arrow is going to point away from it if it's a reactant. So here's a clip on how these work.
Many important biological molecules are made of repeating subunits called monomers. When many monomers join, the result is a polymer. For example, amino acid monomers join to form a protein polymer, and glucose monomers combine to form a complex carbohydrate polymer. Biological polymers form by dehydration synthesis reactions. As you can see here, each of the monomers in this reaction has a hydrogen, or H, and a hydroxyl, or OH group. In the course of the reaction, the hydrogen is removed from one monomer and the hydroxyl group from the other. The hydrogen and hydroxyl group combine to form water, and a bond links the two monomers. Hydrolysis is the opposite of a dehydration synthesis reaction. During a hydrolysis reaction, a polymer is reduced to its monomer subunits by the addition of water. In fact, the word hydrolysis literally means to break water. The hydroxyl group from a water molecule attaches to one monomer, and the remaining hydrogen attaches to the other monomer. In other words, water is used to break the bond holding monomers together. Let's do a quick recap. During dehydration synthesis, the monomers join to form polymers, and water is released. The opposite happens during hydrolysis, where water is added to the reaction to break a polymer into monomers.
Somehow crashing when I oops. Okay, so if you're following in the textbook, this is page 67, and turn that light off. So what we see here is the difference between a dehydration synthesis and a hydrolysis reaction. Keeping in mind that dehydration, notice arrows pointing towards water, water is coming out. Hydration or hydrolysis, water is going in as a reactant. The other thing to remember is in synthesis, this is what, building or breaking? When you synthesize something, like a music synthesizer, you're making music. So think about synthesizing as making. So we're making a larger molecule from some smaller ones. So let's say this is a trisaccharide, 1, 2, 3. Tri meaning 3 sugar units, right? We're going to add a monosaccharide to it. So in order to link these two together, the hydrogen of one, the OH of the other go out as water, and now you have a polysaccharide, right? A longer monomer, or a longer polymer. And then in hydrolysis, it's just the opposite. Let's say we have this polysaccharide, we want to break it down. we want to take one of those sugars off. In order to do that, you have to add water. So water is going to be a reactant. We are hydrating in order to lyse. The word lyse means splitting. So sometimes our cells lyse, that is, they rupture. That's what that word means. Hydrolysis, then breaking that word down, hydrating, adding water in order to lysis. Everybody with me so far? Okay, so let's see. On your first test, you are going to have a diagram that looks similar to this. This is in your outline on page 16. And there's 4 questions here. Go ahead and take a few minutes and see if you can answer them. Based on the fact that A is representing these boxes all linked together. So these boxes are representing unit molecules. Here they're all linked together. Here they are broken apart. Okay, this is A for this molecule. B would be the individual molecules, and then D is going in this direction. Is this building or breaking? And then going in this direction is this building or breaking. So take a minute and see if you can answer those questions. There's actually 5 of them on page 16. I left one off on this slide. And then we're going to do a Kahoot quiz to answer these. In order to do the Kahoot quiz, though, you do need to have the page 16 in front of you, because I don't have that image on the quiz. Okay, and our quiz pin is 493610. Okay, anybody else need more time? Anybody still logging on? Got it? Okay. All right, here we go. 5 questions. Again, these are the same 5 questions you see on page 16 of your course outline. So check out the picture that you have in your outline so you can answer these. First question, which letter in that picture represents a unit molecule? Or unit molecules really would be a better question, because there's several of them. Okay, so most everybody got that as B. We'll go over these in just a second. Social Finch in the lead. Second question, which one represents a macromolecule or polymer? All right, good job. Most everybody got that one as A. Social Finch still in the lead. Third question, which letter represents a synthesis reaction? Uh-oh, looks like there's a little confusion on synthesis is building, folks. Again, I'll show you what I mean in just a minute. We'll go over this. Social Finch still in the lead. Question 4, which one would be addition of water? If we're adding water, we're hydrating, right? All right, that's better. So most everyone got that as D. And nobody's beat Social Finch yet. Number 5, is this a dehydration, synthesis, or hydrolysis reaction? This is looking at this letter equation. So if we're looking at a letter equation, A plus B yields C plus water, the arrow's pointing towards water. So that tells you something about reactions and products. Uh-oh, a little bit of confusion there as well. So let's see, we've got congratulations to Funny Snail, Social Finch, and Penguin Rooster. Yes.
What was the answer to the last question?
I'll show you in just a second. I'm going to go over these next. Ah, I keep losing my balance, don't I? My goodness. It just keeps crashing on me for some reason. All right, so let's look at these. So here's the questions, except for number 5, which I forgot to put on here. But so the first question, which letter represents a unit molecule? These are not linked. So these would be the build. Think of building a house. You've got your bricks or your blocks here ready to go. Once you link them together, you've got the house. So A would be the house, B would be the unit molecules. So that's going to be B. Which letter represents a macromolecule? That would be A because these are all linked together. That's a large molecule. Which letter represents a synthesis? Synthesis, remember, is building. So going from these unit molecules to the macromolecule in this direction is building, okay? And which one then would be addition of water? So that would be hydrating or hydrolysis, just the opposite end. So if one side makes sense, remember the other side is just the opposite. So if it makes sense in hydrolysis, you're hydrating, you're adding water in order to lyse or split this house down into its unit molecules, that's this side going in this direction. This is the building. You're putting these bricks together to make the house. Synthesis means building, and in that case, it is a dehydration synthesis, right? Water's going out. Last question had to do with, I don't have it on here, but if you're looking at the last question on page 5, A plus B yields C plus water, the arrow points towards the product, right? So water is going out. That means it's dehydrating. Dehydration synthesis is what that would be. Anybody have questions on that? Everybody good? Yes? Awesome. Okay, so again, you can expect something very similar to this on your first test. It might not be in this exact order, but it's going to have very similar questions. So what we want to do next is go through the different macromolecules and look at how we make them and how we break them, looking at page 17 in your course outline, concept 5.2. So remember, now first we're going to begin with carbohydrates. We said carbohydrates are a source of what? Why do we need carbs in our diet? energy, right? And in fact, if you want quick energy, you could just eat a spoonful of sugar because that is very close. It's not, it doesn't, or table sugar is a disaccharide, but it doesn't require much to break it down. But why is that not great for you? Because if we eat complex carbs, we get a whole lot more nutrition involved. So that's what I want to talk to you about in this section. So carbohydrates are macromolecules. Remember, I mentioned this word saccharide. That means sugar. So a polysaccharide is the macromolecule broken down into monosaccharides, unit molecules. How many of you have heard of the Atkins diet? Couple people, this is old now. How about the ketogenic diet? More people have heard of that. They're kind of based on the same principle. And the idea is, we've heard for a long time now, especially since the Atkins diet came out years and years ago, that Atkins was one of the first people to say, if you want to lose weight, cut out carbs. And it makes sense because guess what? If you're eating too many carbs, your body's going to convert it to what and store it? Fat. So if you want to break down fat, stored fat, if you're trying to lose fat, you take out carbs, your body does just reverse. It's going to convert your fats to carbs for energy. So lipids are our storage form of energy. And that's going to then make you over time lose fat. So you could do two things really. You could cut out carbs and you could increase your energy requirement by exercising. So those are generally two good things to do if you're trying to lose weight. The other thing is though, then they came up with the idea, well, what if you just eat proteins? Because proteins are the one molecule you don't really store. So if you eat excess proteins, you excrete them. And so you can't really get fat on proteins because you're just excreting them. A lot of bodybuilders will take amino acid supplements. Why? Because they're trying to build muscle. But if they're supplying more than they need, they're just going to excrete them. So I had an organic chem teacher who was a bodybuilder, and he said to me, taking amino acid supplements is really just like taking or making expensive urine because you're just excreting it. However, if you're trying to lose weight, it does work because you're getting all your calories from protein primarily. But here's the thing, if you were to just do nothing but amino acids, and people did this at one time, they would go on strict protein diets where they did nothing but drink amino acid shakes and nothing or eat amino acids, nothing else. Then you're going to run out of energy and you can die. So what happens is and this happens in starving situations too, or people who have eating disorders, they just stop eating and your body goes through all of its carbs, then all of its lipids, and then it will actually start pulling from stored proteins, start cannibalizing essentially your own tissue, and you end up dying of what? What muscle is gonna start breaking down that could kill you? What's the most important muscle in your body keeping you alive? Your heart, exactly. And so people often were dying of heart attacks. So you have to be careful with that. So that was what the idea here is. But if you go back and read Atkins' diet, he originally said, and this is true, that with the introduction of sugar mills, we really started eating way more carbs than we maybe need. Because if you go to most vending machines, for instance, it's loaded with carbohydrates. You might get a bag of peanuts, which has some proteins, but so we tend to eat too many carbs, and if we eat too many carbs, and if we eat the wrong kind of carbs, we suffer all kinds of other problems that we're seeing a lot of these days. Things like adult onset diabetes, obesity, cardiovascular problems, all kinds of issues. So you have to understand what are good carbs, what are bad carbs, what of these carbs should you be eating if you're eating carbs at all. And by the way, it's almost impossible to be on a no-carb diet because all foods have carbohydrates. So even if you're eating nothing but steak, you're still getting some carbs. But anyway, so how many of you have heard the terms glycemic index and glycemic load? Okay, so a few of you. So this is an important number now that we're starting to see, and in fact even labels are starting to, in some cases, put these on there. And it tells you what kind of effect these carbohydrates have on your blood sugar and in turn your insulin. Because what Atkins, his issue was, if we're loading our bodies up with simple sugars, we have a blood sugar spike, and that causes insulin, which converts glucose to glycogen to be released, which is okay, but after a while, if we keep bombarding our cells with sugar, we keep having these insulin spikes up and down, we can develop insulin resistance. We don't react to it anymore. It's not that we're not producing insulin, because adult onset diabetes, you're producing insulin, you're just not responding to it. And some kids are born where they don't even have insulin, which is the hormone that converts glucose to glycogen. They don't even have that, so they have to take insulin injections. But later on in life, if you keep on overloading your body, especially with plain old sugar, you keep getting these spikes, and over a period of time, you can develop insulin resistance. So here's a little bit about understanding these numbers and why they're important.
I'm Dr. Russ, and a member of Harris Teeter's Your Wellness Team. Today I'm going to discuss the terms glycemic index and glycemic load, and why understanding these terms may help you lead a healthier life. You may have heard the terms glycemic index or glycemic load being mentioned when your doctors discuss nutrition and health. They're helpful dietary concepts once we get down to basics. The glycemic index is used to classify foods based on how quickly they cause a rise in blood sugar upon being eaten. When high glycemic index foods are eaten, there's a rapid rise in blood sugar followed by a significant release of insulin, causing blood sugar levels to fall, creating fatigue and hunger. Consistently eating high glycemic index foods may lessen your body's sensitivity to insulin over time, leading to type 2 diabetes and other illnesses. Sugar and white bread are considered reference foods and have been assigned a glycemic index of 100 because they both cause a rapid rise in blood sugar levels after ingestion. All other foods are assigned a proportionately lower value from 1 to 99 based on how they affect blood sugar compared to sugar or white bread. Low glycemic index foods are digested more slowly, resulting in a gentle rise in blood sugar, followed by a more moderate release of insulin, thereby helping to maintain consistent blood glucose levels and lessening fatigue and hunger. Glycemic load takes the concept of glycemic index a step further, offering a more accurate reflection of the impact eating a specific food has on your blood sugar and insulin levels. The glycemic load takes into account the relative amount of carbohydrate the food contains in an average serving. As an example, watermelon has a glycemic index of 72, which is pretty high, but it's mostly made up of water and contains relatively little carbohydrate, so its glycemic load is only between 4 and 7. Now your blood sugar may go up rapidly after eating watermelon, but it shouldn't go up very much, since there's not much carbohydrate present in watermelon to be converted into sugar in the first place. On the other hand, half a bagel has a glycemic index similar to watermelon at 72, but a much higher glycemic load of almost 26, thus a bigger sugar load for your body. There are many reference lists that detail the glycemic index and glycemic load of your favorite foods. And both glycemic index and glycemic load are helpful guides when choosing healthy carbohydrates. But you can't determine whether or not a food is healthy for you based solely on these numbers. They're useful concepts, but the quality and concentration of nutrients found within a given food have to be factored in as well. I hope this helps clear up any confusion around glycemic index and glycemic load for you. Be well.
To watch the other segments of this video series,
Okay, so if we look at then our carbohydrates, as I said, the prefix saccharide is used to refer to these carbs. We're going to start looking at our monosaccharides, and for those we have 4 that I'd like you to be familiar with. Ribose and deoxyribose, these are actually 5-carbon sugars. They are made of a 5-carbon ring that we'll see in a minute. And those are the building blocks for nucleic acids. So when we talk about DNA and RNA, the D in DNA is for deoxyribose, which is a sugar. Ribose means sugar, and plain old ribose for RNA. And then we have our 6 carbon sugars, glucose and fructose, that I'd like you to remember. Those are very important. They're used in assembling many larger carbohydrates, and those are 6 carbon sugars. They have the same molecular formula, C6H12O6. In other words, they have 6 carbons, 12 hydrogens, and 6 oxygens, but they have different structures. So we call these isomers. Isomers are compounds with the same molecular formula, but different structures. So when you see this M, think of isomers, same molecular formula, not to be confused with isotopes, if you remember that term, where we said they have the same atomic number, the same number of protons, but different weights. So carbon 12 and carbon 14 were isotopes, same element, just different weights. Isomer is the same molecular structure, but different, they're the same molecular formula, but different structures. And these are often drawn as carbon rings, which we'll see in just a minute, but here's a clip on carbohydrates.
All carbohydrates are built from molecular monomers, or subunits called sugars, that contain only carbon, hydrogen, and oxygen atoms. The typical sugar has a backbone of 3 to 7 carbon atoms. Most of these carbon atoms have a hydrogen group and a hydroxyl group attached to them. Thus, the general formula for sugars is CH2ON, where N is the number of carbons in the backbone. It is from this formula that carbohydrates derive their name, which literally means carbon and water. When dissolved in a watery environment, such as the cytoplasm of a cell, the carbon backbone of a sugar usually circles up into a ring. It is in this ring form that sugars are linked together by dehydration reactions to make larger carbohydrate molecules. Carbohydrates fall into one of 3 categories, depending on the number of sugars they contain. Carbohydrates, such as glucose or fructose, that consist of a single sugar monomer, are called monosaccharides. Sucrose, lactose, and other carbohydrates that contain 2 sugar monomers are called disaccharides. Starch, glycogen, cellulose, and other carbohydrates made out of long chains of sugars are called polysaccharides. Glucose is the most common monosaccharide and one of the most abundant sources of chemical energy in the living world. Glucose is the sugar found in the highest concentration in the blood of animals, and our own central nervous systems are critically dependent on glucose for energy. But glucose molecules are also the building blocks for the polysaccharide cellulose. Cellulose is the major structural material in the trunks and branches of trees. Glucose's chemical formula of C6H12O6, or CH2O6, is shared with fructose and galactose. However, the 3 have different chemical structures, giving each a different taste. Monosaccharides, such as glucose and its relatives, have a short lifespan in the cell. Most are broken down to provide energy or linked together by dehydration reactions to form disaccharides or polysaccharides. 2 other important monosaccharides are ribose and deoxyribose, each of which have 5 carbons. The 2 molecules are identical, except that as the prefix deoxy implies, deoxyribose molecules have one oxygen less than ribose molecules. Ribose and deoxyribose form critical parts of RNA and DNA molecules respectively. RNA and DNA are critical in passing the blueprints of life from cell to cell and from generation to generation. Disaccharides are formed by linking two monosaccharides. Cells, especially those of plants, use disaccharides to store and or transport energy. When an organism needs energy, disaccharides are broken apart into their monosaccharide subunits by hydrolysis. Sucrose and lactose are two common disaccharides. Each molecule of sucrose, or table sugar, has one glucose and one fructose molecule. Sugarcane and sugar beets produce and store huge amounts of sucrose and are harvested commercially to produce table sugar. Many female mammals produce lactose or milk sugar by adding a galactose molecule to a glucose molecule to provide energy for their nursing offspring.
How many of you have heard of high fructose corn syrup? So yeah, so that's a bad part. So there's been a whole lot of problems associated with high fructose corn syrup, and it was found in all kinds of products. So read your labels, and if you see high fructose corn syrup, don't buy it. It's supposedly taken out of most products now, but it's still there. Some of the problems, besides just increasing weight gain, blood pressure, diabetes, heart inflammation, insulin resistance, heart disease, all kinds of stuff associated with high fructose corn syrup. So again, if you can avoid that, that would be good. In general, monosaccharides are not the kind of way you want to get your carbs because they're what we call empty calories. They're just, sure, it's good energy, it's quick energy, and if you're a runner and you want to hurry up and get some energy before a run, maybe that would be one thing. Or if you're in the hospital and you're not allowed to eat, they would give you a glucose solution because then it doesn't need to be hydrolyzed, right, broken down, it's already in its unit molecule. Then you would need these simple sugars, but most of the time, the more complex the molecule, the better, because there's more nutrients and other things there. As I mentioned, monosaccharides are usually in the form of carbon rings, as we see here. This is deoxyribose, part of DNA, and this is ribose. These two are the 5 carbon sugars, and here's our 6 carbon sugars, glucose, fructose, and another one I didn't mention, galactose, which is involved in producing milk sugar. So these are all isomers. They have the same molecular formula, C6H12O6, but structurally they're different. And if you were to really look at how these carbons are arranged and what's attached to what, you would see the structures are different. Not something I'm going to ask you about, but that's by definition what an isomer is. For the disaccharides, I ask that you know these 3. Sucrose, which is a transport form of sugar that's used in plants. We harvest sucrose, that's our form of table sugar. So most of you, I think, are aware that we have a pretty big sugar industry here in South Florida, and that we harvest sugar cane, right? Cane is the stem of the plant, and that's where we have the most sucrose because it's a transport form of sugar, which means when a plant makes its own sugar through photosynthesis, and that usually happens primarily in the leaves. But all cells, just like all our cells, need carbohydrates, same with plant cells. So the way they get it to the rest of the plant is through the stem. And that's why we're going to harvest the cane or the stem of the plant to get the most sucrose. Lactose is milk sugar. How many of you have heard of lactose intolerance? People who can't tolerate lactose, they're not allergic, folks. So if you have a food allergy, you either break out in hives, or you might have some swelling or a rash, something like that. Intolerance means you cannot hydrolyze it. What is that again? Building or breaking? Breaking. Lysis is breaking. And so in other words, you don't have the enzyme lactase. Usually that's the problem to digest lactose down into its monosaccharide unit molecules. So what happens? You just pass it through. So you are intolerant to it. A lot of people, babies are born a lot of times without that enzyme. Once it kicks in, they can tolerate lactose. Maybe some people develop it later in life, they stop making the enzyme, and some people never make it, so they have to be be lactose free. Maltose is a seed sugar. If you eat sunflower seeds, pumpkin seeds, you'll get a lot of maltose. And we do digest that again, just like the rest. These are all disaccharides. 2 sugar units, di meaning 2. And then we have our polysaccharides, poly meaning many. Starch is a common one, and we get a lot of starch in our diet through starchy vegetables like what? What's a good example of a starchy vegetable? Potatoes, exactly. So plants store their energy as starch. In the potatoes or tubers, the roots have these storage sacs called tubers. So if you're eating tuberous vegetables, that's starchy vegetables. So we store our excess carbs as what? In our bodies. We store it as fat. And plants store it as starch. And also all plants have cellulose. Cellulose is a complex carbohydrate that we do not digest, and yet it's really good for us to have in the diet. And so if we look at a plant cell, and we'll do this next week in lab, we're gonna be getting the microscopes and looking at plants, and we'll see this rigid cell wall made of this fibrous material called cellulose. There's lots of it in celery, hence the name celery after cellulose. And notice it's long chains of these carbon rings. It's very fibrous. Why is fiber good in the diet? Anybody? Anybody know why fiber is good? Nobody wants to say? Yeah, it pushes stuff through. It keeps you regular. And why is that important? You may have heard if you're on a high fiber diet, it might help protect against colon cancer. What does your colon do? It collects feces. What's in your feces? Waste. What's in waste? Probably toxins. Do you want it sitting there very long? No. The longer it's sitting there, the longer your colon cells are exposed to these toxins, a higher chance it could change the cells, causing mutations possibly, and causing colon cancer. So you always want to stay regular. So if you're not regular, add more fiber to your diet. There's also other benefits of fiber, which this clip will show you next.
It's in your salad. You found it in your snacks.
Dietary fiber is
Start that over.
Fiber is in your breakfast cereal, it's in your salad at lunch, it can even be found in your snacks.
dietary fiber is the parts of the plant that are not digested nor absorbed by our body.
Despite that, Mayo Clinic dietitian Kate Zaratsky says fiber in both soluble and insoluble form plays several important roles.
Both soluble and insoluble fiber can help with weight control because fiber helps us feel full.
Soluble fiber, which dissolves to a gel in water, can help slow digestion, lower bad cholesterol, and regulate blood glucose. Insoluble fiber is bulky, draws in water. It promotes the comfortable movement of food through your digestive system.
So it'll help keep you more regular.
To be more regular and healthier, add fiber to your diet with whole grain products, fruits and vegetables, beans, and seeds and nuts.
And drink plenty of water.
Fiber works best when it absorbs water in your body. For the Mayo Clinic News Network, I'm Chet Olson.
Okay, so there's some benefits of fiber. Another polysaccharide you may or may not have ever heard of is something called chitin. This actually makes up the exoskeleton of many of our arthropods, which have to molt, that is, shed that exoskeleton because as they grow, their skeleton doesn't grow with them. They have to grow a new skeleton. So whether it's crabs, shrimp, insects, all of them are arthropods with an exoskeleton. We have an endoskeleton, right, inside our body that grows with us. We don't have that problem. Chitin we actually can digest, so if you wanted to eat the entire lobster, you actually could. It's not very palatable though, but it is handy in the medical field in making strong and flexible surgical threads that decompose after the wound or incision heals. So that's nice to have. And that wraps up our polysaccharides. Remember, the carbs then are for quick energy. So our storage form of energy is what? lipids or fats, right? You probably call them fats, but there's actually several different groups of lipids that we're gonna look at. So lipids are one class of large biological molecules that do not form polymers. They have this unique feature of having little or no affinity for water, which means they don't mix with water. So what does that mean? Are they hydrophobic or hydrophilic? Hydrophobic, exactly. And the three groups we're gonna look at are phospholipids, fats, and steroids. A lot of times people hear of steroids and they think hormones are steroids. Well, some hormones are steroid based, some pharmaceuticals are steroid based. This is just a type of lipid, that word. And so we'll talk about what makes a steroid in just a second, but first, the question here, just like with carbs, what are good fats and what are bad fats? And which fats should you be eating, if at all? Here's a clip on that.
Here's the skinny on fats. Not all fats are created equal, and not all of them are bad for you. In fact, there are good fats and there are bad fats. First, the bad. There are two types of unhealthy fat in foods: saturated fats and trans fats. Saturated fats can increase your chances of cardiovascular disease and raise your cholesterol levels. And saturated fats may increase your chances of getting type 2 diabetes. Saturated fat is found in things such as palm oil, eggs, milk, and meat. Then there's trans fat. Not only does trans fat increase a person's total cholesterol level, but it actually lowers the so-called good HDL cholesterol levels too. And it can increase your risk of cardiovascular disease. Trans fats are found in things like margarine and some meats. But there are good fats too. Monounsaturated fats found in avocados, nuts, and olives lower your cholesterol levels. And polyunsaturated fats found in corn oil, nuts, and fish are known to decrease the risks of heart disease. So, how do you avoid the bad and get the good? Your best bet: read food ingredient labels. They contain valuable information that will help you make better decisions about what you eat. Maintaining a healthy lifestyle can be easy if you know your facts about fats. Go to BaylorHealth.com/healthcast for more ideas, podcasts.
Again. Must have some kind of incompatibility thing going on here. So. That's that. Okay, one thing I forgot to mention when we were talking about carbohydrates, when you're trying to figure out what are good carbs and bad carbs, general rule of thumb is to stay away from white carbs. So, just pure sugar, of course, white rice. If you're gonna eat rice, you should eat maybe brown or whole grains in general rather than white bread. So that's a general rule. When it comes to good fats and bad fats, well, there's a few things to think about. First of all, what kind of fat is it? Before we get into saturated and unsaturated good fats and bad fats, I want to first talk about phospholipids. We have a whole chapter on this molecule. It's very, very important because every single cell membrane is made of phospholipids. And no matter who you are, you have phospholipids. And the unique thing about phospholipids is there's this phosphate head, which is hydrophilic, which means it mixes with water, and then you've got two fatty acid tails, which are hydrophobic, meaning it doesn't mix with water. So when you put this molecule in water, what's going to happen? Is it going to be attracted or repelled? And so both, exactly. And so what happens, and the theory is that when these molecules were bathed in water, the hydrophilic phosphate heads faced either out towards what we call extracellular water, water outside our cells, and then the intracellular water, water inside our cells, and then the hydrophobic fatty acid tails all clustered on the inside, making up this lipid bilayer. Bi meaning two layers of lipids. And this is how the theory is that this is how the cell membranes were formed. And so we do see that our cell membranes are all made of phospholipid bilayers, as you see here. And again, the hydrophilic heads facing towards the water, either outside the cell or inside, and the hydrophobic tails clustered away. So we do have a whole chapter on cell membranes. If for now you just remember that cell membranes are made of phospholipids, we will come back to that later. Our second group are fats. And remember, fats are made of two unit molecules, fatty acids and glycerol. Fatty acids vary in their length, their number of carbons, and the number of locations of these double bonds. All fats have the major function of storing energy. But when we look at a typical fat, we can see here's a glycerol molecule, and here's a long fatty acid tail. These can consist of hundreds of carbons all linked one to another by these covalent bonds, right? Notice these are all single covalent bonds. This is palmitic acid, and we call it an acid because here's that acid group I mentioned, the C double bond OH. When we are building this molecule, oftentimes what happens is 3 fatty acids will link to the one glycerol, and we will have something called a triglyceride. If you've ever had your lipid panel checked, one of the things they're looking for are triglycerides. How much triglyceride is in your blood, because it's a sticky component. So most fats and waxes are sticky anyway. So why is that a bad thing? Because these sticky molecules can actually clog up your arteries and cause problems with blood flow. So when we look at these fats, we want to first identify, are they saturated or are they unsaturated? Which one's the bad fat? Saturated or unsaturated? Saturated. So most of you have heard, yes, stay away from saturated fats. Why is that? And what's the difference? Well, a saturated fat gets its name because it has the maximum number of hydrogen atoms attached to that carbon skeleton. Notice every carbon has a hydrogen, so we say it's chock full of hydrogen or saturated. Whereas unsaturated fats are missing some hydrogens, and instead the carbon double bonds, and that makes it sort of bend. This is an unsaturated fat. Because it has the bend like that, it makes it liquid at room temperature, whereas saturated fats are solid at room temperature. Is this a saturated or unsaturated fat? Saturated. Every carbon has a hydrogen attached. That's a saturated fat. Good examples of saturated fats are things like butter and lard. These are of animal origin, and the problem with that, not only are saturated fats sticky, but they also have cholesterol, which is another type of fat, sticky fat, that can clog up arteries as well. So the idea is, well, what if we stay away from animal saturated fats, and instead, because we love butter, we can take an unsaturated fat that is of plant origin, and the first one we used was oleic acid, and it's missing hydrogens. What if we hydrogenate it? That is, add hydrogen to it so that it looks like butter, tastes like butter. I can't believe it's not butter. What is it? It's not butter, it's, what do we call that stuff? Butter look-alike.
Margarine?
Margarine, exactly. So the first margarine was called oleo after the fact that we were saturating oleic acid. And so what we thought we would do, since we're not having saturated fats, here's what can happen with saturated fats. As it says here, it may contribute to cardiovascular disease through plaque deposits. Here we see in yellow lipid deposits. This is the baseline. Here's an artery. And notice that it's getting wider and wider. In 15 months, this person has built up plaque, and that has narrowed the artery. And what does that do to blood pressure? If you reduce volume, increase pressure, increase blood pressure. So that's a bad thing. So we said, okay, what if we take some unsaturated fat? So that's why you hear things like olive oil. Any unsaturated fat is, plant origin fat has no cholesterol for one thing, so that's good. And it also can have beneficial effects on your cardiovascular system instead of the opposite. So when you look at this, is this saturated or unsaturated? Unsaturated. So here's the thing to look for. If you see carbon double bonds or you see hydrogens missing, it's an unsaturated fat. So if you get a test question that says the carbon has more carbon double bonds than this other one, it would be more saturated. The more carbon double bonds are more unsaturated. The more hydrogens missing, the more unsaturated. So what we came up with this idea of hydrogenating fats to make them look and taste like butter. Then what we did is we took an unsaturated fat, as I said, like oleo or oleic acid, and we added hydrogens, making it saturated. So that process is called hydrogenation. But unfortunately, now we have found that the process of hydrogenation converts these, as it converts these fat, it produces trans fats. How many of you have heard of trans fats? So those are now getting a really, really bad rap. So they may contribute more to saturated fat disease or cardiovascular disease than anything. So trans fats, you want to definitely stay away from. They have now taken trans fats out. They were in everything from cookies, French fries, anything that's fried, anything that's baked. They were in there, but now they've taken them out for the most part. So check your labels, make sure it says 0 trans fats, but even when it says 0, they can still have small quantities of trans fats. So they're trying to really get them out of everything. And most of the fast food restaurants today have gotten rid of trans fats. You also hear about essential fatty acids, those that you need, things like omega-3s, and people will say, these are good fats, things like fat that you find in fish and flax and walnuts. These are all good fats. These are important because they are required for normal growth, and they are also thought to provide protection against cardiovascular disease. That word ketosis, that's where the ketogenic diet came from. All it's saying is if you're burning fat, you're producing ketones. So in fact, in the diet, I think they even recommend that you check for ketones in your urine. That's just a sign you're burning fat, and that's always a good thing if you're trying to lose weight, right? So ketosis is simply converting fats into ketones. That's how we break our fats down as we digest them. Then we have this third group, the steroids. Steroids are another group of lipids, and they get their classification is based on the fact that they have this 4-carbon ring structure. That's what makes a steroid. Not that it's a hormone. Some hormones are steroid-based, as I said. Some pharmaceuticals, like corticosteroids, you put that, maybe if you have a rash to reduce inflammation, all of those are steroid molecules. But also cholesterol is a steroid. It is in every single animal cell membrane. So we have to have cholesterol. We're animals, so we need cholesterol. We just need it in our cell membranes and not circulating around in your blood. So you'll have if you have your lipid panel checked, that will check for not only total cholesterol, which is how much cholesterol is in your blood, that could clog things up, but also the 2 components that transport our cholesterol, LDLs and HDLs, which I'll get to. But first, a clip on understanding cholesterol.
Cholesterol. Cholesterol is a fatty substance in your blood. You need it to keep your cells healthy. Cholesterol is carried around your body by proteins in your blood. When cholesterol and proteins combine, they form lipoproteins. There are 2 main types of lipoprotein. One is good for your health, the other is bad. Non-high density lipoproteins, otherwise known as non-HDL, take cholesterol from the liver to the cells that need it. Too much non-HDL creates a buildup of fatty deposits which narrow your arteries. This can limit the circulation of blood and oxygen and lead to an increased risk of a heart attack or stroke. This is why it is known as bad cholesterol. High-density lipoproteins, otherwise known as HDL, remove excess cholesterol from the cells and take it to the liver where it is broken down and removed from your body. This is why HDL is known as good cholesterol. Ideally, you need a low level of non-HDL and a high level of HDL. This is so there are enough good guys to get rid of the bad guys. High cholesterol typically has no symptoms, and if left untreated, can lead to heart and circulatory diseases. Anyone can have high cholesterol. It can be caused by eating too much saturated fat, being overweight, or not being active enough. Take control of your cholesterol and find out more about the life-saving research we fund. For more information, visit chf.org.uk/cholesterol.
So as that clip mentioned, even though cholesterol is essential in animals' cells, high levels in the blood may contribute to cardiovascular disease. And the factors that put you at risk for high cholesterol would include high blood pressure, smoking, a family history of premature heart disease, physical inactivity, diabetes, and obesity. So if you donate blood, they will tell you what your total blood cholesterol is, and it should be about the typical number is something below 200 is good. But more importantly is your LDL and HDL ratios. So that you would have to go to your doctor to have checked. So if you have any of those risk factors in your family, you guys are young now, although when you get to be in your 40s at least, most of the recommendations are to start having your blood cholesterol checked, especially if you have a family history, and look at those numbers because you want to keep the low, low, and the high, high. So you want to keep the low, low because that is the lipoprotein that dumps cholesterol into the blood, and the high, high because that's the one that cleans up the blood. So you may even have high blood cholesterol, but if your LDL to HDL ratio is good, then it's still not a problem like it would be if you've got these ratios are off. So you really need the whole thing, and including triglycerides as well. So we are out of time. That wraps up the lipids. When we come back next time, we're going to do proteins and then have that game show review. So don't forget to study as though you're taking the test. If anyone has questions, I'll be here for a couple minutes. The rest of you I'll see in lab in 10 minutes. Please don't sit at that first table when you walk in because you can't see the board, but any table other than that is fine. And I'll see you in 10.